On the morning of September 1st, 1859, a British amateur astronomer named Richard Carrington was in his private observatory south of London, sketching a large cluster of sunspots. It was routine work. He had been doing it for years. Then, at 11:18 in the morning, something happened that no one had ever witnessed before. Two brilliant white patches of light erupted from within the sunspot cluster, so intense they were visible in broad daylight through his telescope's solar filter. They expanded rapidly, moved across the solar surface, and faded within 5 minutes. Carrington had just witnessed the first solar flare ever recorded by a human being. He had no idea what he had seen. The sunspot cluster Carrington had been sketching was enormous, one of the largest ever observed at that point in recorded solar science. Large sunspots indicate intense magnetic activity on the solar surface. The Sun, in September 1859, was at a period of heightened activity. The conditions had been building for days. The flare was the detonator. The flare had ejected a coronal mass ejection, a billion-ton cloud of magnetized plasma, directly toward Earth. This was not unusual. The Sun produces CMEs regularly. What was unusual was the size, the speed, and the direction. This one was aimed squarely at us, and it was moving faster than almost anything the Sun had ever produced. A typical CME takes 2 to 4 days to reach Earth. This one arrived in 17.5 hours, the fastest transit ever recorded. It hit Earth's magnetosphere at approximately 4 a.m. on September 2nd. The compression of the magnetic field was immediate and violent. What happened next unfolded across the entire planet, simultaneously. Across the northern hemisphere, the sky erupted. Auroral displays of extraordinary intensity blazed in shades of crimson, green, and white, so bright that in the northeastern United States people could read newspapers outdoors at midnight by the light of the sky. In the Rockies, gold miners woke at 1 a.m. believing it was dawn and began preparing breakfast. In Cuba, Colombia, and Hawaii, latitudes where the aurora is essentially never seen, the sky turned red. Across the Caribbean, people who had never heard of the Northern Lights stared at a sky that appeared to be on fire. The geomagnetic disturbance was so severe it had pushed the auroral oval deep into the tropics. This had never been recorded in living memory. The world's telegraph network, the Internet of 1859, began failing simultaneously across multiple continents. Operators at stations from London to Washington reported their instruments behaving strangely. Needles deflected without commands being sent. Currents flowed in lines that were supposedly inactive. Then came the sparks. At telegraph stations across the US and Europe, geomagnetically induced currents overwhelmed the equipment. Sparks shot from instruments. Recording tape ignited. Operators received electric shocks through their keys. Some were thrown from their chairs. Several stations caught fire. The geomagnetic storm had turned the global telegraph network into an uncontrolled electrical system, conducting currents from the magnetosphere itself. In one of the more remarkable footnotes of the night, operators in Boston and Portland, Maine discovered they could disconnect their batteries entirely and still send and receive messages. The auroral current flowing through the telegraph lines was sufficient to power transmission on its own. For 2 hours, the geomagnetic storm ran the US telegraph network without human electricity. Modern geomagnetic storm intensity is measured on the DST index, a measure of the disturbance of Earth's magnetic field. The strongest geomagnetic storm in the modern instrumental record is the Quebec event of March 1989, which registered approximately -589. The Carrington event is estimated at -850 to -1,600. Nothing in the recorded instrumental era comes close. When Carrington heard about the global telegraph chaos and the spectacular aurora, he connected it to the flare he had sketched the morning before. He published his observation alongside independent confirmation from another British astronomer, Richard Hodgson. Carrington was cautious. He wrote that one swallow does not make a summer. But the connection he identified was correct. The solar flare had caused it all. A coronal mass ejection doesn't damage things by burning them. It induces electrical currents in anything long and conductive on the ground. Power lines, pipelines, railway tracks. In 1859, the only long conductive infrastructure was telegraph wire. Today, the planet is wrapped in millions of kilometers of power transmission lines, fiber infrastructure, and undersea cables, each one a potential conductor. On March 13, 1989, a geomagnetic storm roughly a third as powerful as the Carrington Event struck Earth. In Quebec, Canada, the entire provincial power grid collapsed in 90 seconds. 6 million people lost electricity for up to 9 hours. Transformers were damaged as far away as New Jersey. It was a fraction of what 1859 produced, and it shut down a province. In late October 2003, a series of powerful solar storms struck Earth during what became known as the Halloween storms. Over 15 satellites experienced anomalies or permanent damage. Air traffic was rerouted away from polar regions. Power outages hit Sweden. The FAA issued alerts warning that GPS accuracy could not be relied upon. The storms were significant and still far below Carrington scale. On July 23, 2012, the Sun produced a coronal mass ejection that NASA scientists later assessed would have registered a density of approximately minus 1,100, comparable to the Carrington Event. It missed Earth by 9 days. Earth had passed through that region of its orbit 9 days earlier. The CME screamed through empty space where our planet had been and was detected by a stereo spacecraft watching from another angle. A Carrington-scale event today would induce geomagnetically driven currents across every long electrical conductor on Earth. High-voltage transformers, the critical nodes of the global power grid, are particularly vulnerable. They are enormous, custom-built, and not kept in stock. Replacing a damaged extra high-voltage transformer takes between 1 and 3 years. A Carrington event could damage dozens simultaneously across multiple continents. Above the atmosphere, the storm would be worse. Satellites in low Earth orbit would face radiation exposure far exceeding their design tolerances. GPS navigation would fail globally. Communication satellites would be damaged or destroyed. The internet relies on a network of undersea cables whose repeater stations are vulnerable to induced currents. Modern aviation, shipping, and military systems all depend on infrastructure that did not exist in 1859. In 2013, Lloyd's of London estimated the economic damage of a Carrington-scale event to the United States alone at between $600 billion and $2.6 trillion, roughly 3 to 15% of annual GDP. The National Academy of Sciences projected that recovery could take 4 to 10 years, not 4 to 10 days, not 4 to 10 weeks, 4 to 10 years without a functioning electrical grid. Researchers have estimated the probability of a Carrington-scale event hitting Earth in any given decade at somewhere between 1 and 12%. Over a century, the cumulative odds become difficult to dismiss. The Sun has produced such events before. It has produced them recently. 2012 simply didn't hit us. There is no physical reason it cannot happen again. The question is when, not whether. Richard Carrington went back to his observatory after the storm passed and continued sketching sunspots. He had no way to know he had witnessed the defining event of solar science. No way to know his name would be attached to it 165 years later. The sun rose the following morning exactly as it always had. In 1859, that was enough. We have since built a civilization that requires it to behave itself.